The first module is just sampling processes. Um, Simple analog signals are digitized to prevent the effect of disturbance, interference, and other losses. Digital signals are easily regenerated. So there's a block diagram that they will likely ask, and that is shown here on the left. The input transducer goes from A to D, and then the A to D as in the analog signal is digitized, and then it goes to the source encoder, and then goes to the channel encoder, then goes to a modulator where it's transferred back to an analog signal, and goes through the channel, then it goes back through the demodulator, blah blah blah. In a digital communication system, the source is an analog signal. The transducer converts a physical into electrical signal and is also converting the analog signal into a digital signal. So the source encoder then takes this data and tries to compress it and reduce the redundant bits. And then when there is an error, the channel encoder adds those redundant bits back to correct. The modulator modulates, obviously, and the digital signal is turned into analog to get the signal to actually transmit through the channel. And the demodulator, channel decoder, source decoder do the exact opposite of all of these processes. So that's pretty much the only thing you need to know about the block diagram if they do ask it. And then the next sort of question that's going to show up is sampling. Sampling is just taking instantaneous values of a signal at different points in time. So let's say there's this continuous signal called x of t. It's sampled at a rate of ts. That is like every ts seconds it's sampled. Then sampling frequency is f equals 1 by t, obviously. So this derivation is something that they will ask as well. So there are three key steps to this derivation. The first is you consider an impulse train, which is delta of t is the summation of delta of t minus nts. And then you see two graphs here below that. Those graphs are the impulse train and the analog signal. So what you do is you take those two and you multiply them in the time domain, and then you get the resultant signal here. That resultant signal is then represented as g of t equals x of nts delta of t minus nts. So what you do is you take the Fourier transform of this. Now, obviously, the actual derivation has a lot of additional steps, but I think this is practically enough for what you need to do in the exam. All you need to remember is that the Fourier transform comes to 1 by ts of x of omega plus x of omega minus omega s plus x of omega plus omega s. So what this represents is a center frequency wave there and one on either side and then just stretching out, a negligible waveform stretching out on both ends. So this quantity that you see between omega m and omega s, where omega m is a maximum frequency, is omega s minus omega m. That's the gap. So for the two spectrums to not overlap, the distance obviously has to exist. So the condition there is that for these waves to not overlap, omega s minus omega m has to be greater than omega m. That is like coordinate wise. And if you rearrange that inequality, it becomes omega s is greater than 2 omega m. So that is the sufficient condition for your waves to not overlap. And if it is equal, it means that they're touching each other. Because if omega s minus omega m is equal to omega m, then it just means both of them are in the same point. So you again rearrange that inequality, it becomes omega s equals to omega m. So in both of these cases, we'll notice that there's no overlap. There is a continuous signal can always be reconstructed through a low pass filter. So there is one condition in which a low pass filter can't reconstruct it, and that's when omega s minus omega m is less than omega m. Or again, rearranging the inequality, omega s is lesser than 2 omega m, then the spectrum overlaps and you get a graph as shown on the top right. So for one thing to note about these signals is that these signals are all band limited. So when these band limited signals need to be reconstructed, the sampling rate should therefore be at least twice the maximum frequency. So you just replace omega with f because, well, they're directly proportional to each other. So this is what is known as the Nyquist rate. So if you sample the signal as exactly at two times the maximum frequency of the wave, then that sampling frequency is known as the Nyquist frequency or Nyquist rate, and 1 by fs is ts, as we already noted. So there's another thing to consider. When the signal is not band limited, then high frequency components are going to be introduced. And when these interfere with low frequency components, something known as aliasing happens. So the basic thing to remember here is that on top of the waveform or spectrum that we've already drawn, there's going to be a similar spectrum that interferes with the performance of this. And this is just a bit of theory that they'll probably ask. So there are two ways to prevent this. The first is run the spectrum through an anti-aliasing low-pass filter, or the second is you raise the sampling rate and take it slightly above the Nyquist rate. So these are two ways in which you stop aliasing. The first question is pretty straightforward. Find the Nyquist rate for 3 cos 50 pi t plus 10 sin 30, 300 pi t minus cos 100 pi t. So here, each sinusoidal signal is given in the form of a cos omega t. So we already have omega given to us, which is 50 pi, for example, in the first frequency component. So since omega is 2 pi f, we convert it. So 50 pi divided by 2 pi is f, or f for the first component for that matter, and it becomes 25 hertz. The second one is 300 pi by 2 pi, which is 150 hertz, and then 100 pi by 2 pi becomes 50 hertz. And the maximum of these is obviously 150. So the Nyquist frequency is going to be 2 times that, which is 300 hertz. The second question is we need to recall sync for that, or sine C, however you like to pronounce it. So sinc of x is sine of x divided by x, or you could say sine of pi x divided by pi x if you don't want to normalize the function. So that becomes the expression then becomes sine of 200 pi t divided by 200 pi t plus sine square of 200 pi t by 200 pi t squares. And then you have the frequency, which is 100 hertz, but we also have sine square theta is 1 minus cos 2 theta by 2. So the second term that we have a sine square of 200 pi t, we can't just take the frequency as f2. We have to convert it to a sinusoidal wave, which is not a square wave. So you convert sine square theta to to a cos term, and then you take the theta from that. And because theta gets converted to 2 theta in the cos term, you essentially don't need to do the entire conversion. You can just take theta is 2 times whatever the theta already exists, and it becomes 400 pi, and that becomes the equivalent frequency. Therefore, you do 400 pi divided by 2 pi, your second frequency component becomes 200 hertz. That is your greater frequency component. Then the Nyquist frequency becomes 2 times that, becomes 400 hertz. Right. So the next question is find the sampling rate for a fairly simple signal again. So here is just a basic trigonometric identity. Cos of A, cos of B is cos of A plus B plus cos of A minus B divided by 2. You convert those and you get cos of 1500 pi t plus cos of 500 pi t as the main expression. And then you take the greater one of those and then you divide by 2, which gives you 750 hertz. So the sampling rate needs to be a minimum of 750 hertz times 2, which is 1500 hertz. If they ask for the Nyquist frequency here, or the Nyquist sampling rate, your answer would be equal to 1500 hertz, but the sampling rate can be anything greater than or equal to the Nyquist. The next is cos 10 pi t plus cos 30 pi t is sampled at 20 hertz and reconstructed with LPF with cutoff frequency 20 hertz. So it's a different type of question. And what is given here is usually three things. They will give you the expression, they will give you the sampling frequency, and they'll give you the cutoff frequency, and they'll say, oh, you want to reconstruct this. So the requirement here is that, well, there's a bit of complexity, but there's a very simple formula. The maximum frequency is something that you find first. So FM is equal to 30 pi by 2 pi, as we already do, that's 15 hertz. And we've already been given the sampling frequency as 20 hertz and the cutoff frequency as 20 hertz, as I've written there. So the only formula that you need to keep in mind here is that you need to test for all frequencies NFS plus or minus FM. Here, N is like any integer, but usually you'll want to stick to checking with 0, 1, minus 1. Beyond 2, it should get too high unless the cutoff frequency is very, very high. So two examples here. The first one is n equals 0. So you'll notice that when n equals 0, then fs doesn't matter and it only becomes fm, which is 15 hertz. And again, it becomes plus or minus fm, so minus 15 hertz also exists. Similarly, you check for n equals 1 and n equals minus 1, and you get about 6 frequencies. But you'll see that I tried checking n equals 2 here, and it's just too high of a value to even matter to us. So since the cutoff frequency is fc equals 20 hertz, we want to take ones that are between minus 20 hertz and plus 20 hertz because those are the limits on both ends. So here you'll see that there are only 15 hertz, minus 15 hertz, and 5 hertz and minus 5 hertz. Here we don't consider negative values because it's a band pass signal. So we take the positive values, which are 15 hertz and 5 hertz. These are the only ones that stick within the limit of minus 20 and plus 20. Similarly, the second question, we have the same parameters given to us. We have FM, we have FS, we have FC. We have the same formula, we have the same application, and we get two frequencies which are 100 hertz and minus 100 hertz. Again, we ignore the negative frequency, and the only frequency that's present in the in this reconstructed signal is that of 100 hertz. Now, there's a bit of derivation here for quantization, but this is looked at in the second module, so we can just ignore that part. The part to look at here is theory. So sample signals are quantized to return discrete values. So these are then put into encoders. So the step size or the integral quantization levels is given by the difference of the maximum amplitude and the minimum amplitude divided by L, where L is the number of levels. And we'll note here that the number of levels is given by log 2 of L. So, sorry, the number of bits is given by log 2 of L. So let's say you have 8 levels, then your number of bits is going to be 3 because log 2 of 8 is 3. The intuition for this is that the number of levels is always 2 power the number of bits. So if you have 3 bits, then 2 cube is 8, which means you have 8 levels. So that is a formula in general. And this is how quantization works, right? So if you have a signal and you're trying to quantize it, then it's always going to get approximated to the midpoint of the zone that it is in. So if you have 8 levels and your Vmax and Vmin are 20 and minus 20, then your step size is, as you see, 5. So there's also a difference between the original analog signal and quantized signal, which is known as the quantization error. So obviously, when you approximate the signal to an integral value, there's going to be a difference. So as this number of levels grow, then the step size decreases because the number of steps you need is far more, and the quantization error naturally falls. There are two types of quantization here. The first is uniform, which is you have the same step size everywhere. The second is non-uniform, where your step size keeps changing. So we won't really look at non-uniform quantizers, but for uniform quantizers, it's useful to keep in mind there are two types. The first is mid-rise, which is um, the origin falls at the midpoint of a rising edge. So you'll see that here on the left side of the left graph, you'll see that the origin falls at the center of a rising edge. Similarly, mid-tread, your origin falls at the center of a treading edge, I guess. But yeah, whatever that edge is called. Basically, you go horizontal and your origin falls at the center of that. So these are two different types of quantizers. And that's probably it for this module.